Imagine a mathematical problem, maybe something you bumped into way back in school, but scaled up, way up, so complex, so daunting that for centuries it was basically considered, well, unsolvable.
Right.
By the standard ways of doing things, a problem where even brilliant minds would say, okay, here, our methods just stop working.
Hmm.
But what if that wall, that supposed dead end, wasn't really an end? What if it was actually, I don't know, a signpost pointing to a totally new path, a completely different way of thinking about it?
That's a great way to put it because, yeah, for a very long time, the world of polynomial
Yeah.
equations, these are fundamental. I mean, they pop up everywhere in science and engineering.
Sure.
They've carried this historical baggage, especially you get to the higher degrees.
Hmm.
We figured out the simple ones, quadratics, cubic,
Yeah, those are manageable.
but the complexity,
Yeah.
it just shoots up incredibly fast. It really felt like we hit these hard limits on finding, perfect exact answers.
Hmm.
But now, well, now there's a new approach emerging,
Hmm.
one that really promises to kind of shatter those old limitations.
Okay, intriguing. So today we're going to dive deep into exactly that. It's a groundbreaking mathematical method known as Ezoudi's theorem. And our mission here really is to unpack how this theorem is changing the game, how it's redefining what we mean by finding exact symbolic solutions for these really high degree polynomials.
Yeah.
We're even going to tackle a monster, a degree 18 polynomial. We want to understand how this theorem works, the mechanics of it, why it actually matters, and why it's considered such a significant step forward in maths.
That's the plan. Our mission, as you said, is to explore how Ezoudi's theorem gives us these precise solvable roots for polynomials that, I mean, traditionally we just threw up our hands and said, okay, exact methods won't work here.
Right.
And doing that, I think we'll see really clearly how powerful it is compared to the numerical methods, the approximations that have been the standard toolkit for so long.
Okay, let's unpack this then. Polynomial equations, we all remember them maybe vaguely from algebra, right?
Mhm.
Things like x squared plus 2x plus 1 equals 0.
Classic quadratic, yeah.
Yeah, simple enough, solvable. But the moment you start increasing that highest power of x, that's degree the complexity, it doesn't just climb steadily, it explodes. It's exponential.
Absolutely.
So when we talk about a degree 18 polynomial, we're not just talking something a bit fiddlier than a quadratic. We're talking about a level of complexity that historically was just seen as this enormous hurdle, a real beast.
Exactly. And to really get why Ezoudi's theorem is such a big deal, you kind of have to look back. You have to see the history. For centuries, mathematicians wrestled with these higher degree equations.
Mm,
Then, back in the 19th century, you had figures like Ruffini and especially Niels Hendrik Abel.
Abel, right? Abel's
Sean's
theorem.
theorem, yeah. It delivered what felt like the final word on the subject for many. It famously states there's no general algebraic solution using radicals.
Okay, what does using radicals mean in simple terms?
Good question. It means using just a finite sequence of basic arithmetic, adding, subtracting, multiplying, dividing, and taking nth roots, like square roots, cube roots, and so on.
Got it. So, no universal formula using just those basic operations for solving any polynomial of degree 5 or higher.
Precisely, for the general case.
Yeah.
And that theorem, Abel's theorem, it had a profound impact. It basically created this perception, this barrier that said exact solutions stop here beyond degree 4 for the general polynomial.
So, yeah, for anyone who knows their math history, Abel's theorem felt like, well, like a law of nature almost, a mathematical mic drop. Game over for finding exact answers for these more complex beasts in general, which left people thinking, okay, if we can't get the exact solution, what can we do?
Right. And that's where the practical need led to the rise of numerical methods. Given that finding exact general formulas seemed impossible for these higher degrees, mathematicians, scientists, and engineers, they turned to approximation techniques.
Like Newton's method. Remember that one?
Newton's method is a perfect example. It's very widely used. These methods, they don't aim for the absolute mathematically pure answer. Instead, they work iteratively. They generate a sequence of numbers that get closer and closer to the actual root.
So they zero in on it.
They zero in on it, yeah. And they're incredibly valuable tools. They're used everywhere in physics simulations, engineering design, economic modeling, because for a very long time, they were really the only practical way to get any kind of answer for many complex problems.
And they've obviously been hugely successful, letting us build bridges and send things into space and all that. But approximation isn't the same as exactness. What are the key differences? And maybe what are the downsides of relying only on approximations?
That's the crucial distinction. Numerical approximations, powerful as they are, have built in limitations. First off, they are, just by their nature, error prone.
How so?
Well, the more complex the polynomial, especially high degrees, the more calculations you need. Each calculation might introduce a tiny error, maybe from rounding, maybe from the method itself only being an approximation, and these errors can accumulate.
Ah, like compound interest, but for errors.
Kind of, yeah. And they carry the risk of rounding errors, specifically because computers, which do these calculations, can only store numbers to a finite precision. Little bits get chopped off, usually it's fine, but sometimes those tiny errors can snowball.
Okay.
But the absolute most critical point is this: numerical methods cannot guarantee exact values. They can get you incredibly close. You might get an answer accurate to 30 decimal places, which sounds perfect.
Sounds pretty good to me.
It often is, but it's still not the true mathematical value. It's an estimate.
Mhm.
Think about the square root of 2. A numerical method might give you 1.41421356. Very close.
Right.
But the exact symbolic value is just score T2. That symbol represents the pure precise value. Ezouidi's theorem, that's what it's aiming for. It's aiming for the score T2, not just the 1.414. It wants absolute precision.
Gotcha. So it's a fundamental difference in the kind of answer you're looking for.
Exactly.
Which brings us back to Ezouidi's theorem. So what's really fascinating here, you're saying, is that this theorem just completely changes the game. It redefines how we even approach solving these high degree polynomials.
Yes. It's not just a slightly better numerical method, not an incremental improvement. It's a fundamentally distinct, structured process.
Right.
And the output isn't an approximation, it's the exact symbolic solution.
Wow.
It's like, everyone was trying to climb the sheer cliff face of the mountain, getting approximations of the summit height. And Ezouidi found a hidden path, maybe a tunnel, that goes straight to the true summit itself.
Okay, so for those of us, maybe myself included, who kind of absorbed the idea that, general fifth degree polynomials, let alone 18th degree ones, were fundamentally unsolvable in that exact algebraic sense. What's the core aha moment
Right.
here? How does this Ezouidi approach get around that apparent limitation set by Abel?
That's the million-dollar question, isn't it?
Yeah.
The breakthrough is really in the methodology. Ezouidi's approach cleverly bypasses the specific limitations that classical algebra, the kind Abel was dealing with, ran into.
Oh,
Well, Abel's theorem is correct. It says there's no general formula using only radicals for degree 5 or higher. But Ezouidi's method isn't trying to find a general radical formula in that classical sense. It uses a different toolkit, a different process. It introduces this novel recursive process.
recursive, meaning it builds on itself, step by step.
Exactly, step by step. And this process, it turns out, can find the exact values, even for polynomials that might have radical roots.
Mhm.
But it arrives at them through this different structured pathway.
Mhm.
It essentially demonstrates that there are other mathematical structures and methods outside the scope of what classical algebra considered for solvability by radicals that do work. It found a new route where the old signpost said dead end. It reveals a deeper structure to these polynomials.
Okay, so it's not necessarily disproving Abel, but finding a completely different way to the same goal, the exact route that Abel's framework didn't account for.
That's a very good way to put it. It sidesteps the limitations.
So the bottom line is this isn't just about getting a slightly better number or finding a clever trick for one specific equation. It's a systematic, structured process that bypasses those centuries old roadblocks. It's not giving us a numerical approximation, it's revealing the precise, solvable roots in their pure symbolic form.
Correct. It's a completely different category of solution. Exactness, not estimation.
Okay. Mind blown already. Now we understand the promise of exact solutions, but I'm sure everyone listening is now thinking, okay, but how? How on earth does this actually work? Let's get into the mechanics. How does this theorem pull off this seemingly impossible feat of precision, especially given the history we just talked about?
Right? The how is where the real ingenuity lies. The core of Ezouidi's theorem is this recursive process we mentioned. Think of it like um, meticulously dismantling a very complex watch piece by piece, understanding how each part fits, and then reassembling it perfectly.
Instead of just measuring the outside dimensions.
Exactly. The method involves systematically breaking down the polynomial into these, let's call them manageable components. At each step in this recursive breakdown, it calculates certain symbolic coefficients. And the key is these coefficients are inherently exact. They're derived symbolically, not numerically.
So no approximation errors can sneak in during the process.
Precisely. That's the crucial advantage. This recursive definition and calculation of coefficients prevents any estimation errors from creeping in and accumulating. This is what allows it to derive those final, precise, symbolic values for the roots, rather than just getting close.
That makes a lot of sense. It's about maintaining perfect integrity at every single step. Now, the source material we looked at, it includes a core mathematical formula that kind of drives this engine. It looks, well, it looks pretty dense at first glance.
Formulas often do.
Yeah. It's something like SK1R equals sum. CKRKNS is 0S0RK 0R SR1R.
Mhm.
Now we definitely don't need to, perform the calculation live on air.
Probably
But
wise.
can you break that down for us? Conceptually, what are the pieces doing? What's the role of this formula in the process?
Absolutely. Let's demystify it a bit. While the notation looks intimidating, the idea behind it is actually quite elegant. Think of it as a recipe, an iterative recipe for building the exact solution components layer by layer.
Okay, a recipe. I like that.
So those scale one terms on the left, those are the symbolic coefficients we're trying to find at each step of the recursion. These values are directly linked to the roots of the polynomial in a very specific way.
Mhm.
And the crucial part, again, is that every single one of these is calculated symbolically. No numbers rounded off, no estimates made. They stay exact throughout.
So these S values are like the exact, perfectly measured ingredients for our final solution.
That's a great analogy. Perfectly measured ingredients. Then you have the Cn and k bit inside the sum. You might remember these from math class as binomial coefficients, things like n choose k.
Right, combinations.
Exactly. They're basically specific whole numbers that act like multipliers, combining the other terms in a mathematically precise way. They ensure the structure holds together correctly as we build up the solution, again, without introducing any approximations.
Okay, so they're like precise instructions in the recipe.
Kind of, yeah. Then you have SSR, KIR. This involves a base coefficient, is SOIR, which is related to the polynomial's initial coefficients raised to a specific power. It acts as sort of anchor or reference point adjusted at each step.
And the last piece, SR1R.
That part refers to earlier's values, coefficients that we've already calculated in previous steps of the recursion.
Yeah.
This is what makes it recursive. Each new value explicitly depends on the exact values derived before it. It's building upon the previous perfect steps.
Ah, I see. So it's constantly using the exact results from the previous stage to calculate the next exact result.
Precisely. It maintains that chain of exactness,
Yeah.
which naturally leads to the important question.
Yeah.
Okay, we calculate all these exact values. How do they actually give us the roots of the polynomial at the end of the
Yeah,
whole?
that's the payoff, right? How do we get from these S things to the X we're looking for? Well, let's make this really concrete. The source material you shared gives this fantastic, if slightly terrifying, case study, a degree 18 polynomial.
Ah, yes, the big one.
It's huge. I'll just read the first few terms to give everyone a feel for the scale, but please, nobody try to write this down unless you really want to. It starts PAX 8 live by 18 by 17 plus 153 by 16, 8, 16 by 15. And it just keeps going with this large coefficients all the way down to a constant term.
It's definitely a beast. It has 19 terms in total. And in the source material, those coefficients, the numbers multiplying the powers of x, are represented as L0Q through L17Q. Those are the specific inputs we feed into the Ezouidi theorem machinery.
Okay, so we feed this monster polynomial into the process. The method then starts applying that recursive formula, calculating the K1R values step by step for K0, K1, K2, all the way up to K18 for this degree 18 example. What actually happens? What do these Viseros values turn out to be for this specific complex polynomial?
This is where it gets really, really interesting and, frankly, quite elegant.
Yeah.
As the method churns through these recursive calculations, something remarkable happens. Almost all of those symbolic says coefficients, they simplify down to exactly zero.
Wait, really? Zero?
Exactly zero. We find that 0R, S1R, S2R, all the way to S7R, they all equal zero. And then skipping one, C9R, S10R, up to 16R, also all zero.
Wow. So out of 18 potential Zes coefficients calculated through this complex process, most of them just vanish. They turn out to be nothing.
Precisely. They evaluate to exactly zero through the recursive steps. It's quite astonishing.
So which ones don't vanish? Which ones are left holding the information?
Only two survive, essentially. Only two crucial coefficients, S8R and the final one, S17R, turn out to be non-zero. The calculations, which are purely symbolic and exact, yield specific values for these. ACR comes out as minus 48619 times 18 raised to the power of 9.
Okay, a large number, but exact.
A very large number, but perfectly exact, expressed symbolically. And S17R comes out as 408, 600, and 621 times 18 raised to the power of 18.
Again, enormous, but precisely defined.
Yes. And this pattern, this vanishing of most coefficients, isn't an accident or an approximation. It's a direct result of the structure revealed by the recursive calculation. It's incredibly significant because it means we've maintained exactness throughout, avoiding any possibility of approximation errors building up. And we've ended up with just two key symbolic values that hold the essence of the polynomial's root.
Okay, that's a huge simplification. So let's connect the dots. What does this dramatic simplification, all those zeros, just two non-zeros values left, actually mean for solving our original intimidating degree 18 polynomial? How does it help us find the roots?
This is where the sheer power and elegance of the theorem really hit home. Remember, the polynomial can be expressed not just with its original coefficients, LHQ to L17Q, but also in terms of these calculated as coefficients. So Px equals by 18, IDR by 17, plus S1R by 16, LHQ alternating signs, all the way down to plus S17R equals 0.
Right, that's the alternative form.
But since we just discovered that almost all those eds values are 0,
Oh, then almost all those terms just disappear.
exactly. The equation collapses. It drastically simplifies down to just three terms. Px, you said, equals always implicitly there. Then the term involving nr, which comes with a minus sign in the alternating pattern. So ADA by 18, 8 down 1, which is by 9. And the final constant term plus S17R. So the whole thing becomes might 18 brain, IDR by 9 plus S17R equals 0.
Wow. From that 19 term monster down to just three terms, that is incredible.
It is. This reduction is the core payoff of Ezouidi's method. It transforms a problem that looked impossibly complex into something much, much more manageable, purely through symbolic manipulation.
And looking at that simplified,
You said C9R, S10R, up to 16R, also all 0.
wow. So out of 18 potential z coefficients calculated through this complex process, most of them just vanish. They turn out to be nothing.
Precisely. They evaluate to exactly 0 through the recursive steps. It's quite astonishing.
So which ones don't vanish? Which ones are left holding the information?
Only two survive, essentially. Only two crucial coefficients, S8R and the final one, S17R, turn out to be non-zero. The calculations, which are purely symbolic and exact, yield specific values for these. ACR comes out as minus 48619 times 18 raised to the power of 9.
Okay, a large number, but exact.
A very large number, but perfectly exact, expressed symbolically. And S17R comes out as 408, 600, and 621 times 18 raised to the power of 18.
Again, enormous, but precisely defined.
Yes. And this pattern, this vanishing of most coefficients, isn't an accident or an approximation. It's a direct result of the structure revealed by the recursive calculation. It's incredibly significant because it means we've maintained exactness throughout, avoiding any possibility of approximation errors building up. And we've ended up with just two key symbolic values that hold the essence of the polynomial's root.
Okay, that's a huge simplification. So let's connect the dots. What does this dramatic simplification, all those zeros, just two non-zeros values left, actually mean for solving our original intimidating degree 18 polynomial? How does it help us find the roots?
This is where the sheer power and elegance of the theorem really hit home. Remember, the polynomial can be expressed not just with its original coefficients, LHQ to L17Q, but also in terms of these calculated as coefficients. So Px equals by 18, IDR by 17, plus S1R by 16, LHQ alternating signs, all the way down to plus S17R equals 0.
Right, that's the alternative form.
But since we just discovered that almost all those eds values are 0.
Oh, then almost all those terms just disappear.
Exactly. The equation collapses. It drastically simplifies down to just three terms. Px, you said, equals always implicitly there. Then the term involving nr, which comes with a minus sign in the alternating pattern. So ADA by 18, 8 down 1, which is by 9. And the final constant term plus S17R. So the whole thing becomes might 18 brain, IDR by 9 plus S17R equals 0.
Wow. From that 19 term monster down to just three terms, that is incredible.
It is. This reduction is the core payoff of Ezouidi's method. It transforms a problem that looked impossibly complex into something much, much more manageable, purely through symbolic manipulation.
And looking at that simplified form, by 18, 8 by 9 plus S17 are equals 0. Hang on a second. That looks familiar somehow. It's not quite a standard polynomial in X anymore, it feels like something squared.
You've got it. That's the next brilliant insight. Look at the powers. 18 and 9. 18 is exactly twice 9.
Ah, so by 18 is the same as by 9 too.
Precisely. So we can rewrite that simplified equation as by 9 2, A2R by 9 plus S17R equals 0.
That's amazing. It's basically turned into a quadratic equation, not an X, but in by 9.
Exactly right. If you just temporarily think of y ups by 9, the equation is just y2 ace ry plus S17R equals 0. And we all know how to solve quadratic equations.
The quadratic formula from high school.
The very same. We can use the quadratic formula to find the exact values for CR in S17R.
Okay, so we use the quadratic formula on this y equation using our exact symbolic values for CR and 17R. What does that give us, and how do we get back to X?
Okay, so first we calculate the part under the square root into the quadratic formula, the discriminant but adapted for this equation. The source calls this S1R, and it's calculated as S1R equals 9 is 8R2 plus 4 S17R.
Using the exact values we found earlier.
Using those exact huge but precise values. 486, 19, 86, 19, 2 plus 4, 8 by 4, 86, 21, 9, 18, 18. When you work through the arithmetic symbolically, this comes out to another exact, though negative number. S1R equals dash 236,361,267 by 1818.
Okay, another exact symbolic value.
Then the quadratic formula tells us that y, which is by 9, is equal to a squared S1R2. Or rather, since S1 is negative, let's write it as a squared S squared if S1R2, where the term under the square root is now positive.
Right, involving the square root of that massive positive number, 236,361,2677 by 1818. And the S1R value all still exact.
All perfectly exact. So now we have the exact symbolic value for by 9. The very last step is just to find x itself. If by 9 equals that expression, then x must be the ninth root of that expression.
The ninth root, okay.
Which leads us to the final exact symbolic roots for the original degree 18 polynomial. They involve taking the ninth root of the Santiago-Sixavian Swiss R2. And because taking roots introduces complex numbers, the full expression for the roots involves complex exponentials, specifically terms like 2 by 9 multiplied by the ninth root result. The source gives the form as x equals 1 plus. Then ask squared is 2363 is going 26 was 267 in 18, 2 by 9. There's a slight adjustment involving 1 plus that likely comes from a transformation used, but the core is solving for by 9 and taking the root.
So the roots are complex numbers expressed perfectly precisely using these calculated whole series values and mathematical constants like pi and I.
Exactly. And the absolute crucial takeaway here is that these roots we've derived, they are exact. They're expressed in this pure symbolic form. They're not approximations. They're not subject to the potential pitfalls, the rounding errors, the accumulated inaccuracies that inevitably come with numerical methods.
It's a guaranteed precise answer.
Yes. This approach ensures that we can find these roots exactly, even for these incredibly high degree polynomials that classical methods couldn't handle exactly and numerical methods could only estimate.
That's genuinely remarkable. It feels like finding a hidden structure within these complex beasts.
It really is. It reveals an underlying simplicity if you use the right tools to look for it.
So let's zoom out a bit now. We've seen the how in quite some detail with this degree 18 example. Let's talk about the why it matters. If we connect this back to the bigger picture, what are the broader implications of being able to get these exact symbolic solutions instead of just very good approximations?
The implications are actually quite profound, I think, and they stretch across many different fields.
You mentioned earlier that for many things, like building a bridge, maybe an approximation to 15 decimal places is perfectly fine. So where does this absolute precision really make a critical difference?
We'll think about fields operating at the extremes of scale or complexity. Quantum physics, for instance. The behavior of systems at that level is governed by incredibly precise mathematical relationships. Tiny errors in calculation could lead to predictions that are just wrong. Or consider high precision engineering designing components for spacecraft, particle accelerators, advanced optics.
Okay, yeah, where tolerances are incredibly tight.
Exactly. In those contexts, even small rounding errors accumulating in a complex simulation could potentially lead to a design flaw, a deviation from the required performance, or even failure. Cryptography is another area. Many modern cryptographic systems rely on the mathematical properties of large number and complex equations. Having exact methods might reveal structural insights, for better or worse, that approximations would completely miss.
So precision is key in certain demanding applications. What about understanding? Does an exact solution tell us more than a really good approximation?
I would argue strongly that it does. An exact symbolic solution often reveals the underlying structure of the problem in a way that a string of decimals just can't. You can see the relationships between parameters. You can see how the roots depend on the coefficients in a fundamental way. It provides deeper theoretical insight.
Like seeing the blueprint versus just measuring the finished building.
That's a good analogy. Numerical approximations might obscure those elegant mathematical relationships, the inherent symmetries or patterns, while the exact solution lays them bare. This can lead to a much deeper understanding of the system you're modeling.
And maybe even lead to new discoveries if you understand the structure better.
Absolutely. Overcoming a long-standing perceived limitation, like the impossibility stemming from a narrow interpretation of Abel's theorem, does more than just solve one type of problem. It opens up entirely new avenues for mathematical research. It makes us question other perceived boundaries. It fundamentally reshapes our understanding of what might be possible. It encourages people to look for new methods, new perspectives.
What stands out to you the most about this? Is it the mathematical elegance, the practical potential, or something else?
For me, it's perhaps the intellectual audacity, the willingness to challenge a long held belief. Not necessarily to say the old belief was wrong in its context, but to say, is that the only way to look at this? Is there another path? It's a testament to persistent curiosity and truly inventive thinking. It shows how finding a completely new methodology can unlock problems that seemed locked forever.
It really highlights how mathematics isn't static, isn't it? It's constantly evolving as people find new ways to think.
Precisely. It reinforces that idea beautifully. Ezouidi's theorem doesn't invalidate classical algebra or Abel's theorem within their defined scope, but it elegantly bypasses those limitations by introducing a different framework, a different set of tools. It confirms that there's always more to learn and that exploring multiple perspectives, multiple methodologies is how we deepen our understanding.
What an incredible journey we've taken today, really. We started with this daunting image of an 18th degree polynomial, something that sounds like it belongs purely in the realm of abstract theory or supercomputers running approximations.
Mhm.
And we've walked through how Ezoudi's theorem, with its clever recursive process, can systematically dismantle that complexity and arrive at elegant, exact solutions. The core takeaway for me is really hammering home that fundamental difference between approximation and exactness, and why accessing that exactness is such a powerful leap forward.
I agree. It truly showcases the ingenuity possible within mathematics. This recursive approach, systematically calculating these exact symbolic coefficients, peeling back the layers. It feels like it unlocks hidden truths about the structure of these equations, truths that were obscured by the sheer complexity when viewed through older lenses.
It really makes you wonder, doesn't it? And this brings us maybe to our final thought for you, the listener. What other problems out there, problems that currently seem unsolvable or intractable, maybe in mathematics, maybe in science, maybe in engineering, finance, or even just complex systems in your own work, what other challenges might yield if we approach them with entirely new ways of thinking? Perhaps looking for structured, recursive approaches where we currently only see complexity.
That's a provocative thought.
Maybe some of the walls we perceive around problems aren't solid barriers after all. Maybe they're just waiting for someone to find a different kind of key, a different perspective, like Ezouidi did for high degree polynomials. Something to definitely mull over.